Good afternoon, this is Schweitzer. We're going to talk about the differences between strong acids and weak acids and calculation typically of the pH of a weak acid. So what is the difference between a strong acid and a weak acid? Well, it turns out that a strong acid, let's review that. Lost ourselves a little marker there. Okay, and alright, so what does strong acid do? Dilute strong acid goes to completion. So it would just be like H plus and X negative. This guy here would just be H plus, X negative, H plus, plus, X negative, H plus, X negative. So a weak acid goes to what we call equilibrium, and typically speaking, they're very much reactant favored. So in this case, whenever we track this, its K value is a ratio of the products over reactants. Since there's lots of reactants, we have a very small K value. So lots of reactant, very little product. So we might even just show it like this. Okay. I know there's some product there, but when you start to see some of the levels of how small the product is, then you might realize why we don't show them. Could you show one? Okay, you can. Maybe. I may not. But you surely wouldn't want to show two. Same thing goes here. I go concentrated weak acid. H plus HX, 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 HX. I'd probably leave it like this. But if you feel the need, you could do one H plus and maybe one X negative. Keep in mind, when you take a beaker or maybe drink something vinegary or whatever, or you stick your finger in some acid, okay, what's causing this thing to burn your finger or whatever? It's the H plus ions. So here, do you see any H plus ions? Well, we got one. Okay. Do we see any here? Well, we got one. So here we got a bunch. So in this case, keep in mind that the HX here is not acidic until it actually produces an H plus ion. So there you go. That's important to note. All right, so acid-base conjugate pairs. So we got to realize that and acids and bases, they work together. They go back and forth, really. So this is my acid. Okay, and this is what I call it's called the conjugate base. Conjugate base. And you should realize that this is the same substance. Okay, it's the same chemical. It's just given this guy an H plus ion. So now this guy, its conjugate is this guy. So conjugate, sometimes I like to use the word neighbor. It's like the same atom, but just on the other side. And in this situation, we're going to call an acid, okay, an acid is what we sometimes refer to as an H plus donor. And a base is what we call an H plus acceptor. And that's another way of sort of describing the interactions between an acid and a base. So this would be my acid, this would be my base, this would be my conjugate base, and this would be my conjugate acid. Okay. Write the reaction for hydrolysis of ammonia. Well, this is ammonium. So what would be the reaction going this way? That's what bases do. So again, I'd sometimes think of it, if whoever has the H plus is the acid. Whoever doesn't have is the base. This guy has the H plus, an extra one here. Therefore, this is the acid. But once it loses it, it becomes this guy. Now it's a base. It can accept one. So the ammonia can turn around, grab onto a base. Now it's going to get that from water. and it's going to produce NH4 plus OH negative. And if you want to make this look a little more complicated, you could say, okay, well, let's put the two reactions together. Okay, NH4 plus water yields NH3 plus H3O plus. These two reactions going back and forth, looks like this cancels out, this cancels out. The water is just water, and we got water producing these guys. Of course, these guys will annihilate each other, and we all just sort of cancel out. Okay, they all just sort of, they are the reverse of each other, so the reverse should kind of cancel each other out. So a solution is a solution of ammonia or ammonium acidic or basic? That's the question. If they cancel each other out, which one is it? Well, it turns out we have this idea of strength, and that's something that strength and concentration are two things that will affect this, and it's something that we'll be talking about here momentarily. Okay, strength meaning how vigorously can you push towards products, how vigorously can you push back towards the other side. Okay, so how do we measure the strength of an acid? Well, we use what's called our K value. It's either Ka or it would be a Kb. Okay. Now the Ka for this thing is the hydrolysis. I've always thought this should be written as KAH to remind us it's the acid hydrolysis, and this is KBH, but they never do that. But it's just one of my things. All right. So in this situation, we have it's going to be NH3 plus H2O yields NH3NH4 plus OH negative, and this is going to be NH4 plus H2O yields NH3 plus H3O plus. This is the reaction that the acid will measure. This is the reaction that the base, Kb, will measure. And whichever value is larger means who's stronger. Very close, but that's it. So again, the Ka times the Kb equals Kw. So this is a teeter-totter, and it balances once again on 1.0 e to the negative 7th. Okay, so this is the teeter-totter point. So who is stronger? So how do we measure the strength of acid? We use the K value. This is the strength, the K value. Who's stronger? I don't know. We have to look up and see who's got what Ka value. Okay, but they both can't be equally strong. One can't push one way, and the stronger than the other one pushes back. I mean, either one pushes hard and the other one pushes weak. They both can't be strong. Okay, so it's kind of a teeter-totter here. So if I have, for example, let's just say this thing here is, I don't know, well, maybe we'll have that value pop up later, but if you give him one of these guys, it would just be the Kw divided by the Ka equals the Kb, and the Kw divided by the Kb equals the Ka. And if you have one, you can solve for the correlating one. Okay. What would be the Ka of an acid where the conjugate base is equally strong? So in that case, it would have to be where the Ka would equal the Kb, and that only happens when the Ka and Kb equal 1.0 e to the negative 7th. Okay. All right. We'll have an example to try some of that in a moment here. Okay, now, so hydrofluoric acid. So what do we need to know to determine the pH of just a plain old solution? Okay, just that. Well, I need two things. I need to know how strong it is, and I need to know its concentration. So those are two things we need to know here. Let's try this out. Okay. Now again, HF I have here as common. It's got a pretty theatrical history, meaning that in Breaking Bad, and you may or may not be familiar with Breaking Bad, but they dissolve a drug dealer with hydrofluoric acid. In Saw 6, yes, Saw 6, they have a torturing device using hydrofluoric acid. So is hydrofluoric acid nasty because of its acidic properties? And the answer really is no. All right? It's not a strong acid. It's a weak acid. And here's the Ka value for hydrofluoric acid. Okay? So in this case, what's the reaction? Well, it's going to be HF plus H2O yields H3O plus F negative. So it's very weak reactant favored. So initial Stoichiometric ratio and in the end, most of my stuff's going to stay here. So is it very acidic? Well, not really, because very little of this stuff is actually going to be placed over here. But this stuff is pretty nasty. H3O plus is nasty, so any amount you get is going to show up. You'll notice it. So how we solve this out? Pretty straightforward. I'm going to use my Ka expression here equals the concentration of H pluses, that's this guy, times the concentration of F negative over the concentration of HF. Just so you know, that's this guy. And, okay. So, with that being said, here we go, HF, this is 0.1, not playing a role, 0, 0, minus X plus X plus X, 0.1 minus X, X, and X. Of course, you know that plugging these guys in will equal 6.6 e to the negative fourth equals X times X over 0.1 minus X. Now, it's not that difficult to solve this out, but because of this such a small value here, we're going to use our shortcut rule. 6.6 e to the negative fourth equals X squared over 0.1, multiplied by 0.1 and square root. And this will give you my X concentration. This might seem complicated at first, but you'll find that it never varies. It's always the same. 6.6 e to the negative fourth divided by, or I should say, times 0.1. And then we're going to square root this guy. And I get 0.0081. 0.0081, I believe, and that's moles per liter. Of course, we know that number on our teeter-totter of 1.0 e to the negative seventh, that this thing is in fact acidic. Take the negative log of this value, all right, to find the actual pH. Negative log of this previous answer equals 2.09. All right, so equals 2.09, and this is my acidic pH scale. So a couple things just to kind of notice here. One, we need to have a concentration. All right, we need to have a Ka value. That's really the only two things required to find the pH and or concentration of a weak acid. This tells me how much I start with, and this tells me how much I kick over. Now again, yes, the base, this is weakly basic, but we don't have any of it. In the end, we have a very small amount that, yes, it is pushing back, but that's all kind of wrapped into this calculation. All right, so there we go. There's our math, and hopefully that's something similar. I got one less zero there. We'll see if I made a mistake there somewhere along the line. And I could have, but all right. Again, which ones are weak? Which ones are strong? So of course, remember these are the 6 strong acids. Also, a thing you might know is that the weak acids have a Ka value. The strong acids go 100% to product. They don't need a Ka value. Kas for things that go to completion. Think about that for a second. We have HX plus H2O yields H3O plus X negative. If your reaction goes to completion, then it's going to be H3O plus or times X negative over my original HX, and this guy here is 0. So this is just going to be infinitely large. Okay, so it doesn't do any good. It's like saying if you make $150 in a paycheck and you spend all of it, how much did you spend? Well, you spent $150. You spend all of it. It's not a matter of somewhere in the middle. How do we model a weak acid? And we're kind of circling around here again. How I model weak acids, keep them together. We just kind of do dilute weak acids, and the strong ones we typically just do more of them. Now again, there are H pluses here and there are X negatives, but we don't always show them just for fear of being proportional. It's very much to the reaction side. So showing an H plus and an X negative here would show 30% ionization to product. That's just not what we have. Okay, so it's only reason why they wouldn't show them would be out of fear of having an incorrect proportion. Because, I mean, think of it this way: if you have a K value that is let's say e to the negative fourth, okay, that's not exactly correct, but that's like 1 in 1,000. Meaning you would need to draw out 1,000 of those for one of my actual H plus ions. And that's a fairly strong weak acid. You could have some as e to the negative 10th. That means it's a lot of pictures to be accurate. Okay, so who is stronger, HF or NAF? Okay, so the Ka value for this guy is that. Alright, so once again, we have ourselves HF plus water yields H3O plus F negative. Alright, and this guy is pushing this way, and of course the F negative is pushing back that way. Alright, who's stronger? Well, our teeter-totter, Ka times Kb equals Kw. Let's calculate out our Kb here quickly. Okay, so in this case, the K... do that to me. Alright, so I'll leave it. It'd be 1.0 e to the negative 14th divided by 6.6 e to the negative 4th, and go ahead and calculate. Okay, now this is going to be my Kb for the base. So 1.0 e to the negative 14th divided by 1.0 e to the negative 6th, negative 4th, and I get 1 e to the negative 10th. You might have been able to do that without doing the calculator. Okay, 1.0 e to the negative 10th. Alright, so that means that my Ka value, Ka is this, and I didn't punch that in exactly right. I just did 1. Yeah, it's close. Okay. I can redo that here quickly. It's going to be 1.0 e to the negative 14th divided by 6.6 e to the negative 4th, and I get 1.51 e to the 11th. Okay, so a little bit different, but 1.51 e to the negative 11th. Okay, so this is my Kb, this is my Ka. Who's stronger? Well, the HF is stronger. Why? The K value literally just measures strength. If you ever want to compare strengths, just compare K values. Alright, so a solution contains 0.1 molar HF and 0.1 molar NaF. Remember, concentration and K values determine pHs and H plus concentrations and hydroxide concentrations. What are we? Well, we are acidic. Why? Because we have the same concentration, but my Ka value for the acid's bigger, so I'm acidic. A solution contains 0.1 molar HF and 1 molar NaF. What are we? Well, are we acidic, are we basic, or are we neutral? Well, our concentration of our acid, our base, is up. So that means this forward reaction will be more vigorous. But is the 1 molar enough to counteract the increased strength of the acid? I don't know for certain. I need to do some math on this guy to make sure. And I'm going to say probably not. Now, it might be 10 times more concentrated, but this looks like strength-wise, looks like about 1,000,000 times more strong. I'm thinking we're still going to be acidic, and I know we are. But at this point, if I didn't know, I'd just say this. Can't say for sure. 1 molar HF and 1 molar, 0.1 molar, well, we have more strength and more concentration, so we're going to be acidic. Again, I'm mixing these things together, okay? No HF and 0.1 molar of this, well, because we don't have any of that, all we have is this. You can be the biggest, toughest kid in the block, but if everyone else is just kindergartners, then you're going to be tough. And that's this guy. Okay. So, and then 0.1 molar of this and none of that, well then of course we're just acidic. So understanding how these two things battle back and forth is really it's really the hard thing to kind of understand and really to grip. But once you do, that's the main concept. Calculations, we do them, we forget them. This is more of my big idea, them battling back and forth. All right, let's say example here. We have 0.15 moles per liter of schweitzic acid. Ion acid 3.4%. How do we do this? Okay, well, we have 0.15. And I'm going to do ionizes, so it's minus X. Water's not playing a role. 0, 0, plus X, plus X. So X is 3.4% of 0.5. So 0.15 times 0.034, and what do we get? So I got 0.15 times 0.034 equals 0.0015. 0.0015. 0.0051. So that's this guy right here. So that equals X. So what's the Ka? What's the pH, for that matter? We'll add that in there. Okay. Let's solve it out. Okay, so pH is this guy. I'm just going to plug this guy in here. 0.0051, 0.0051, 0.0051. And what do we get? I'm just going to do this subtraction on my calculator here. 0.15 minus the previous is 0.14. Pretty close, right? So it hasn't changed much. 1449.0051, 0.0051. Take the negative log of this guy to get the pH. Negative log 0.0051 will give me my pH. You'll note that just on that number, 0.051, it's acidic because it's bigger than e negative 7. So negative log 0.0051 is 2.29, which of course is acidic. Okay, what's the Ka value of this acid? So remember, you got to remember that any time we want a Ka value, I need to proliferate my expression. So let's do that right here. The Ka equals the concentration of Sz negative, Schweitzic, H3O plus, HSZ, which means I need to fill this table, which I did. So this is just going to be 0.0051. I'm going to square it because I got two of them. And then 0.1449. And that will equal this guy. Okay. So we got here 0.0051 squaring this thing. Divided by 0.1449. And we get 1.79 equals 1.79 e to the negative, I think it would be fourth. Negative fourth, if I see my calculator correctly. Okay. So now I've got my Ka, I've got my pH. Who's stronger? Well, the acid's stronger because of the Ka value. And it teeter-totters on 1.0 e to the 7th. If Sz negative is stronger, so in this case, it's not stronger. Okay, so is it possible to be acidic if Sc is weaker, then could we ever be acidic? The answer is yes, because there's two factors. There's K, there's also concentration. So we could be acidic or basic, depending on how much we adjust the concentrations. We can't change the K values. We can change the concentrations. And okay, finally, what does it mean if we have if an acid has a larger Ka? Okay, so again, this is the strength, kind of wrapping around again. HA is this guy, HB is this guy. Could HB actually be more acidic? Yes, because concentration and Ka values come to play here. This guy's got a smaller Ka, but so I would really need to crank up the concentration. Now, I'm saying this might be so, the concentration might be unrealistically large at this point, but possible. Okay. Again, reiterating what we just mentioned. Okay. All right. Let's try another example here. Getting towards the end here. If we have a sample of 0.1 molar has a pH of 4.1, determine the percent ionization. So we're not doing a ton of, you'll see, not a ton of calculations here. Just showing simple examples, and you need to practice them. But here's an example. So HX plus H2O yields H3O plus X negative. Initial stoichiometric ratio end. This goes here. What else do you use? Here's the pH, okay? The pH 10 to the negative 4.1 equals the pH. Let's calculate that out. So second log negative 4.1 is 7.9 e to the negative fifth. 7.9 e to the negative fifth moles per liter. And that represents the H plus ion concentrations at equilibrium. That's here, 1.79 e to the negative fifth. And of course, if that's that, well, this is also 1.79 e to the negative fifth. Not playing a role, 0, 0, minus x plus x plus x. And of course, we now know x, which of course you could subtract off of here. But we're going to use our shortcut rule. If you would like, you can. So the Ka value equals the concentration of 1.79 e to the negative fifth squared over 0.1. And you could take it minus the 1.79 e to the negative fifth if you'd like. But you will find your answer will not be a whole lot different. I'm going to square that previous thing on my calculator here and divide it by 0.1, and I'm getting 6.3 e to the negative 6.3 e to the negative eighth. I believe that to be correct. And that would be my Ka value of this particular acid. All right, let's try another example here, if there is one. I believe this is the last question. Just a general idea here. Again, big understanding. We have calculations, true, but there's some understanding stuff. 50 milliliters of a sample of 0.1 molar HA has a pH of 3. 50 milliliters of a 0.1 molar HB has a pH of 4.5. And I could add another one in here, which would be if I had a 0.1 molar has, so let's say HC. I'm going to add this guy in here. So let's say I have a 0.1 molar solution of HC has a pH of 1. Oof. Okay. Which of the following is true about these two acids? This guy's being left out. The Ka of HA is bigger than the Ka of HB. Well, they're the same concentration. More acidic. Yes. HB is stronger than HA. No, because that doesn't jive with the Ka values. Is it possible for HB to have a lower pH than HA? Well, yes, just have to change concentrations. And what about this guy? What do you know about this guy? Well, if it's 0.1 and it's got a pH of 1, that means this guy is a strong acid. Okay. I had a question about that. Either way, I think we'll be stopping there. Keep in mind that this presentation covers concepts and some calculations, but you need to go over what these calculations again. See a few different versions and try them on your own. Okay? Thank you very much.